Okay, so I will be talking about large sets of T designs from groups. And my first slide is a picture 31 years ago. And we can see Doug there and several people we know, and some people are already in the, I'm sure, in the room. And this is the larger picture of that gathering in Stowe, Vermont, back in Vermont in June of '91. So I would like to say thanks to Doug for being a true friend for over 30 years, and for our varied and considerable interaction and collaboration. Doug, you had a significant impact, a more significant impact on our lives. I would also like to thank the Stinson 66 committee for organizing this apparently very strong conference and for inviting me to participate. The talk is based on work done by many people on large sets of designs, of T designs, but in particular, Chuck Cusack, Michael Hurley, and Oscar Lopez, my PhD students, have done part of this work with me. So I begin with talking about group actions, and all group actions, I'm assuming that most people are familiar with group actions. All group actions here will be faithful. In other words, you can think of them as permutation groups. So the first definition is the following. For T greater than 1, we say that the group action G on X is T transitive if the induced action of G on the ordered T subsets of X is transitive. In other words, there's a single orbit on the ordered T subsets of X. The group action G on X is said to be T homogeneous or T star transitive if the induced action of G on X choose T. By X choose T, I mean the T subsets of X is transitive. In other words, a single orbit of G on the T subsets. And for K greater than or equal to 1, a group action is said to be K semi-regular if all the orbits of the action of G on X choose K have length the order of the group. In other words, none of the K subsets can be fixed by any non-identity element in the group. Okay, so some very easy properties. If G act on X is T homogeneous for T greater than 1, and if X is any element of X, then the stabilizer of a point is T minus 1 homogeneous on X minus the point. So in other words, on the deleted set. That's extremely easy to prove. And the second lemma is the following. If I have a subset A of X, when is it fixed by a group element, G? So if G act on X is a group action and G is an element of G and A is a subset of X, then it is fixed by G if and only if A is the union of cycles of G. So here's a little example. If I look at the element G that I have written here, the set A is fixed by G because it's the union of these cycles, 1, 2, 3, 4, and 7, 8, but B is not fixed. Okay, the first here I'm defining what we mean by a simple TVK lambda design. I'm sure that everyone knows this, and I'm not going to spend more time on it because we don't have that much time. Now, by a large set LSN TKV, we mean a collection X comma BI, I going from 1 to N, of TVK lambda designs where the B sub i's form a partition of the complete design X choose K. Now, certain instant matrices have come to be known as the Kramer-Mesner matrices from their 1973 observation that allows us to construct T designs invariant under a prescribed group. You can think of Kramer-Mesner matrices as sort of generalized Rick-Wilson matrices. Here we have a group. Rick-Wilson matrices were simple instance matrices without any group action. Now, so let's define the Kramer-Mesner matrix. Suppose that G act on X is a group action. Suppose that 1 is less than or equal to T, less than K, and less than V, which is the size of X. And let delta 1 through delta R be the orbits on X choose T, and gamma 1 through gamma S be the orbits on X choose K, respectively. Then the T sub K Kramer-Mesner matrix is the R by S matrix, A sub Tk, defined as follows. Aij is the number of K subsets in the orbit gamma J, such that T is contained in K for any particular fixed T in delta I. This is an invariant depending only on the orbits. And you can choose another T, for example, in delta I, and it's easy to prove that there will be, you get the same parameter there. Okay, so a quick picture. If I look at the group action G act on X, it induces an action on the T subsets and also an action on the K subsets. Assume K is bigger than T, let's say. And these are the orbits, delta 1, delta 2, and so on, delta R, and gamma 1, gamma 2, gamma J, gamma S. You connect the T set to a K set if the T set is a subset of the K set. So you get a bipartite graph. And A sub ij is the degree of the, it's the number of edges emanating from a T set in delta I, which end up in orbit gamma J. I think this is quite easy. And of course, there's a dual quantity Bij, and there's some relationships which are easy to consider. Okay, so now the Kramer-Mesner theorem is the following. For a given group action, G act on X, there exists a G invariant TVK lambda design, XB, if and only if there exists a vector U, which is a 0, 1 vector of size S, S being the number of orbits on K sets, satisfying the following equation. A sub Tk times U is lambda J, where J is the O1's vector, the R-dimensional O1's vector. So in particular, the ones, you can think of the ones as specifying the columns of A sub Tk to be added to form vector J. I have a small example. If you take the group G generated by these permutations of degree 9, it turns out to be the dihedral group D3 of order 6. And if you set the parameters TVK lambda to be 2931, so we are searching now, we're looking for a 2931 design. You compute the matrix and it turns out to be this matrix here, and you're looking for columns that add up to the O1's vector. Well, there is the solution I have here indicated by the column arrows, and it turns out there's only one solution in this very specific example. You can see the red ones, and if you look at these columns and add them, you get the O1's vector. So there exists a 2931 design, and in fact, exactly one here. Now, so what if the action G act on X is T homogeneous? Well, let's assume that T is greater than or equal to 1, K is bigger than T, and the action is T homogeneous. Well, then we have a single orbit on T subsets, and possibly more orbits on K subsets. Let's say gamma 1, gamma 2 up to gamma sub S. We can actually prove that in general, if K is less than V over 2, there will be a greater number of orbits than the number of orbits on T sets. Okay, but look at this matrix. It's a 1 by S matrix. And so, by the Kramer measurement theorem, when we now have columns, each column adds to a constant. The first one adds to lambda 1, the lambda 1 times 1, the second to lambda 2, and so on. So in other words, the gammas, the orbits gamma 1 through gamma S themselves are TVK lambda designs, with lambda being this constant here. That's a fantastic gift. We can get T designs immediately. And of course, any union of these orbits is a TVK lambda design, where the lambda is the sum of the corresponding lambdas. And in particular now, we are interested in the case where all the orbits gamma J have the same length. Because if they do, then we have a decomposition of the collection of K sets into TVK lambda designs with the same lambda. So we get a large set of TVK lambda designs. Now, all right, we defined K semi-regular before. So the easiest case to get the same length is to have the action of the group being to be semi-regular. In other words, none of the K sets is fixed by a non-identity element. So what happens? We go back to the previous case and we see that now all the gammas have the same length. The lambdas are going to be all the same. So I get a decomposition into TVK lambda design. So this is now a large set. And of course, N is going to be S, which is the number of gamma, the number of orbits on K sets. And it is V choose K divided by the order of the group, because each orbit has size the order of the group, because this is a K semi-regular action. No K set is fixed by anything but the identities. All the orbits have this size. And so the number of designs is exactly this. Excuse me. And we can calculate the lambda, and it turns out to be this. So we call this G semi-regular large sets of T designs. Okay, now let's look for examples for possible groups that work here. If I look at the group PSL2Q, where Q is congruent to 3 mod 4, an early theorem by many people, well, they contributed in different ways. I didn't go back to the old literature, but Dixon actually quotes these authors. In any case, we know it's very well known that for Q congruent to 3 mod 4, PSL2Q is 3 homogeneous on the Q plus 1 points of the projective line, namely the field elements union the point at infinity. You can think of these also as fractions, right? This is also known as the linear fractional group. When Q is congruent to 3 mod 4, we get a 3 homogeneous group. In addition, we have the following amazing property. Each group element belongs to a cyclic subgroup of order Q plus 1 over 2 and fixes 0 points, or belongs to a cyclic subgroup of order P, where P is the characteristic of the field. In other words, Q is P to the M, fixing exactly 1 point, or belongs to a cyclic subgroup of order Q minus 1 over 2 and fixes 2 points of the projective line. And every group element is semi-regular. In other words, if you take the power of a generator in one of these cyclic subgroups, you get the fixed points, if any, and then every cycle has the same length as every other cycle. So here's a picture which shows what happens. For example, when Q is congruent to 3 mod 4, you get the generator a cyclic subgroup over a Q plus 1 over 2 would have a generator that looks like this. It doesn't fix anything. A generator of order P would look like this. And of course, notice that if P itself is Q, then we have one big single cycle plus a fixed point. And then we have a generator of cyclic subgroups over a Q minus 1 over 2 looking like this. Two shorter cycles of length Q minus 1 over 2 and two fixed points. And of course, elements which are powers of these things. This is what the elements of the group would look like. So now let's see. I'm going to now show you examples where we're going to get a decomposition, large sets of 2KQ designs. Okay, the easiest thing I can think of is to take a Sophie-Germain prime pair, let's say P and Q equals 2P plus 1. Take P to be, of course, not equal to 2. And consider PSL2Q. Now, it turns out, of course, that the safe prime is always congruent to 3 mod 4 in a Sophie-Germain prime. It's very easy to prove, to see. So PSL2Q is 3 homogeneous on the Q plus 1 points of the projective line. Now, if we take any point of X and take the stabilizer of that point, then by lemma 1, H, the stabilizer, is 2 homogeneous now. We go from 3 homogeneous to 2 homogeneous on the deleted set, that is the X minus X, the set Y equals X minus X. Quickly, we can also show, you can calculate the order of H to be the order of G divided by Q plus 1. And because that's the total number of points. And if K is any integer whatsoever between 2 and P, no K subset of Y is fixed by any non-identity element. Therefore, we get an H semi-regular large set LSN 2KQ with N equals Q choose K divided by PQ. Now look at the picture here. How can you have a K if K is between 2 and P? The powers of this element here, for example, elements that fix point, they will always be like that. I cannot get a union of these orbits, of these cycles, to be a K set. And of course, even worse is the top, which is powers of notice, this is just part of the PSL2Q. It's a stabilizer of a point. And okay, now let's take a specific example. Suppose I take P equals 11 and Q equals 23. Of course, then H is equal to 253. And if H is a non-identity element, then H is of cycle type 23. It's a single cycle, or it fixes a point and it's of type 11 square, that is 211 cycles. If you look at all the various Ks from 3 to 10, I don't go farther because 11, of course, 11 sets are fixed by elements of the group. So in all of these cases, you get large sets of TDK lambda designs. Here's the lambda, and here's lambda 1. I mean these as 1 designs. Okay, the 2 designs, of course, are also 1 designs, and here's the decomposition. Now it is not. I would like to skip this perhaps because I'm almost done. I'm asking here what happens when we don't look at Sophie-Germain primes, and this is not necessary. And you get examples quickly where you get a large number of K values for other cases, where, for example, the field is a prime power order, or the dual of that. Now, in this table, I'm looking I will show you in a moment that I'm assuming that I have a little bit more time because we started late.
Yeah, sure.
Okay, so I will show you in a moment that if K is even, well, PSL2Q has elements over the 2 and elements over the 3 in it. Because, well, we have Q and we have Q minus 1 over 2 and Q plus 1 over 2 and Q. So the 3 divides the order of the group and 2 divides the order of the group always. Therefore, there will be elements over the 2 and elements over the 3. But now an element over the 2 either fixes points or it doesn't. But in any case, there are, in the worst case, it fixes 2 points. And for K value up to V over 2, I can take 2 cycles and these two and put them together to form an even number of a subset of K of even size. And therefore, such a subset is fixed by elements of the group. And therefore, we cannot get a semi-regular situation here. So the K values, we cannot have K values of even order. That's why you can see here the K values are odd. And by similar argument, you cannot have 3s. We cannot have K values which are powers of 3. This is true only, this is true for the 3 homogeneous case, and we're looking for large sets of 3 designs, okay? For the 2 case, we can have 3. So what you see here, I put here the possible Q, values of Q, including, notice, including a power of 3, which is 27. And they exist values of K which work even for that. Here I have 5 and 11. But for a typical example, we get many values, many good values of K. If we omit the 3 multiples and the 2 multiples, and there's some others that can be made as unions of cycles. Yeah, we get a huge number of possibilities. Now, we don't, you know, at some point we had argued that there would be infinitely many such large sets, but I never saw the proof. I really am not sure we have a proof yet. And I think we should construct a proof. And I do believe that there will be infinitely many large sets of this type. Here's an example for Q equals 59, acting on 60 points. So here we have PSL 259 acting on 60 points. For K less than or equal to half that, 30, the K subset is fixed only by the identity of G, if and only if K, only by the identity, if and only if it belongs to this set, 7, 11, 13, 17, and 13. And for these values of K, then, we do get large sets. The exception K congruent to 0 mod 3 and congruent to 0 mod 5, you can see how we can not have multiples of 5, because there is a cyclic group of order 30 consisting of, well, generated by an element of with 2 cycles of 30. And if I take an appropriate power, the 6th power, I get an element of order 5, which is semi-regular, and I can make sets of which have size multiple 5, and these are fixed. And so, okay, we have to omit these. So, okay, that's about all, and I hope I didn't take too long. Happy birthday, Doug. And I put here Satsmo because I know someone, my friend Doug, is interested in trumpet, and well, happy birthday, Doug, and great math results ahead. Thank you.